My name is Stephanie Taylor. Sorry, wait, stop. Say that again. Coach me again. Hi, I'm Stephanie Taylor, and I'm very excited to be here for this ASHRAE Tech Hour to talk to you about the intersection of occupant health and indoor air management. I'm really excited to present this to you because the information that we now know puts you, those of you in the building profession, architects, engineers, and builders, in a position to protect human health in the way that we've never really understood before. My journey to you began when I was actually in medical school. So when I was a second-year medical student, I went to New Guinea, Papua New Guinea, and worked in the hospitals for about 4 months. And the conditions were not exactly modern or hygienic. And yet in this country that was on the equator, there were very few surgical site infections or very few infections at all. So I thought, well, maybe back in the 1980s, there was no such thing as a healthcare-associated infection. And yet, when I looked at Florence Nightingale's data back in 1858, during the Crimean War, there were plenty of infections that people were dying from, especially in the winter. Then, back in medical school, I was really intrigued by my mentor, who was the chief of surgery at Children's Hospital. And he would personally clean his operating room. And he told me, as a medical student, that you can never underestimate the importance of the environment in patient outcomes. And that really was impactful for me. So then, fast forward to the early 2000s, I was practicing pediatric oncology. I really worried about the role of the hospital building in my patient outcomes. I had children who were surviving their cancer, surviving chemotherapy, only to succumb to an infection that seemed to me was somewhat related to the building. However, when I tried to talk with building managers about infections, they didn't know how to talk to me. I didn't know how to talk to building managers about HVAC systems or anything about the building. So eventually I pulled myself together and went back to school and got my master's in architecture and worked designing hospitals, working with engineers, so I could really understand the intersection of health and the built environment. Initially, I was working in hospitals and my research related to hospitals, but what I've come to learn is that the trends we're seeing in hospitals, even though patients are more vulnerable than those of us outside of a hospital, and the hospital environment is unique in some ways, the connection between indoor air management and patient healing and staff productivity are lessons that we can apply to all buildings. In 2019, going into the hospital has become a very dangerous proposition. More people die from infections from the hospital environment than people die from car accidents and cardiovascular disease combined. Hospitalization is the third leading cause of death in our country, and those numbers are really reflected around the world. That's alarming and terrible. It's not just infections in the hospital that we're worrying about, but human beings are suffering from infectious organisms that we thought we'd taken care of. Tuberculosis, cholera, and new zoonotic diseases are emerging and re-emerging. In addition to infections, we're seeing more inflammatory disorders, inflammatory bowel disease, things like that. We're seeing a rise in autoimmune diseases, Lou Gehrig disease, lupus, all of these things are increasing. Why is that? Humans are more vulnerable. We're more vulnerable to disease, and these microbes are becoming more virulent. And this is despite the fact that we spend trillions of dollars on healthcare in this country. Our diagnostic and intervention strategies are very, very sophisticated, and yet we're not seeing these changes reflected in improved mortality in our country. What's going on? Well, one thing that's going on, in addition to microbes becoming more virulent, is that human beings have really become homo indorus. We spend 90% of our time in buildings. Centuries ago, we lived in shelters, but those shelters had a lot of communication with the outdoor air, plant life, soil, and so we interacted with microorganisms in a way that we don't anymore. If you remember the oil embargo in the 1970s, where you could only get gas every other day depending on your license plate. Ever since that energy crisis, we've sealed up our buildings, we recirculate the air and filter it. We have much less communication with outdoor air, at least in commercial buildings. So is there a connection between the indoor environment and changing health statistics? Dr. Dickerman, who is an architect who designed the VA hospitals until recently, said, "We shape our buildings, then they kill us." That's alarming. Thankfully, in 2019, we now have brand new tools that we didn't have even 5, 6, 7 years ago that allow us to really better understand human health indoors. So what are these new tools? Let's talk about the tools and some studies that have opened our eyes to the power and the importance of the indoor environment. So prior to 2005, we used tissue culture techniques to look at the bacteria and viruses and fungal organisms, both in our bodies, on our bodies, and in buildings. So for example, if you have a sore throat, you go to your doctor and they would swab your throat with a Q-tip, plate it out on a dish, incubate it, and look under a microscope. So that's called tissue culture. And tissue culture techniques are very valuable. However, they only show us the organisms we're looking for. So as we've started using these new tools, these metagenomic tools, we've discovered that using tissue culture, we only uncovered about 3 to 4% of all the organisms that exist. And actually using metagenomics, our knowledge base continues to expand. So what have we learned? Well, for one thing, we've learned that each human being, each of us, by cell number, is only about 30% human, which is startling. So think about that. You're really more bacteria than you are human. Each of us is an ecosystem walking around with clothes on most of the time. By volume, that means that each of us is about 2 gallons of primarily bacteria. So if you're a germaphobe, don't panic, because most of these organisms are good for us. As I've already said, they help us maintain our health and our equilibrium, our well-being. But when we begin to disrupt these communities of microbes, we see illness, we see inflammation, we see increased allergies, autoimmune disorders, and clearly infections. It's not too surprising to think that as human beings we're indoors, and it takes a matter of minutes before we each leave our microbial signature in a room. So if you're a patient in a hospital, your roommate has left their microbes in the room. People who are in there before you, unless you have absolutely 100% effective sterilization, which the average hospital room does not, you're going to be affected by the previous occupant's microbes. In a house, if you were to rob a house, or if I were to rob a house, I would have to do it within about 5 minutes. Otherwise, a forensic microbiologist would be able to tell lots of things about me. When we do things, either take medication like antibiotics or manage our built environment in a way that restricts the diversity of the microbiome communities, that's when we get into problems. So if you have a garden, you probably wouldn't grow the same crop year after year after year. Biology likes diversity. Ecosystems like diversity. So what does this all have to do with buildings? Okay, well, so if you look out into your room where you're sitting and watching this, you probably don't see microbes floating around in the air, or I hope you don't. If you were to put a petri dish down and let it sit and then incubate that and look under the microscope, you would see probably tens to hundreds of organisms. However, using these new tools, you will see trillions of organisms in your building. So as I'm standing here talking with you, and you're all breathing, I hope, little droplets are coming out of our airways, my mouth, that contain bacteria, viruses. If I have Candida in my mouth, those droplets will contain those organisms. And all of you breathing will be expelling organisms from your airways. Skin flakes are leaving all of our bodies at an amazing rate. These skin flakes carry bacteria. Organisms in your digestive system also communicate with the air, and you can figure out how that works. So there's a very active exchange between human beings, air, and with surfaces. Particles that are on surfaces get resuspended. We live in a three-dimensional world, so it's not just flat as flat. Things in the air resettle on surfaces. So if you, for example, wash your hands, and even if you don't touch anything, any surface or solid, particles from the air can resettle on your hands. And if those particles have a pathogen, a microbe that causes pathology, then your hands are effectively contaminated. And you're not even aware of this. So the air environment is very, very important for cleanliness, for hygiene, and for our health. Again, the University of Oregon has done fascinating research that shows how a building is designed, how the spaces are designed, how they're used, and how they're ventilated actually determines the communities of microbes that survive. And if you think about that, think about the concept of survival of the fittest and how organisms respond to our environment. The indoor environment is now just about the most powerful evolutionary driver of surviving microbes and surviving humans. So the relationship is between the built environment, indoor air, microbes, and human health and disease. So what have we learned about how we ventilate buildings? We've learned that in buildings that have operable windows, the microbial diversity is much greater indoors compared to mechanically ventilated buildings where the building's sealed, windows are sealed, there's high filtration, even great HEPA filter use. We're finding that the indoor air in a mechanically sealed building is much less diverse, but we're also finding that mechanically ventilated buildings have more pathogens than the outdoor environment. So what does that mean? It means that something we're doing in buildings is selecting for the microbes that cause disease. And human beings are in this environment. So we need to begin to take a look at what is it we're doing to buildings, in buildings, that is selecting for these pathogens. A great place to study this question is a hospital. Not just because hospitals are complicated places with lots of microbes, but because we're gathering data on the building occupant. If you've ever been a patient, they wake you up in the middle of the night to get data from you. They check your blood pressure, they might draw blood. Every time you pee, they will test your urine. So we're collecting lots and lots of data from the patient. So let's think about the patient now as a building metric, kind of like the Petri dish in the bed or the litmus paper for the building. What can patient outcomes tell us about indoor air and building management? You might think, well, if you're in a hospital, just having had surgery or with a central line going into your body, that's a different state of affairs than when you go to work. And yes, it's true, we're more vulnerable as people when we're in the hospital. And the hospital can be a virulent environment, but the trends that we're seeing in hospitals we're also seeing in other buildings. So there's lots to be learned from studying patients in hospitals. So I'm going to tell you about a study in that setting as well as some other settings. So back in 2014, I found out about a study going on in a brand new hospital, LEED Silver, about a 300-bed hospital, 24 operating rooms, green roof. All the rooms were single with vestibules, private bathrooms. And a microbiology group was looking at the movement of microorganisms throughout the building, starting from before the hospital was occupied. They were monitoring 10 rooms and 2 nurse stations with parameters such as carbon dioxide, lighting, room air changes, pressurization, hand hygiene, compliance, clinical and visitor traffic in and out of the room. They're taking all these environmental parameters and then looking at the movement of microorganisms. I found out about this study and I said, hey, I'd love to look at patient outcomes in those 10 rooms. So in 2014, I joined a study where a group of microbiologists was looking at the movement of bacteria, viruses, and fungal organisms in a hospital. And they were correlating the movement of those microbes as determined by the metagenomic analysis with indoor parameters. So we looked at In patient rooms, we looked at carbon dioxide levels, acoustics, CO2, room pressurization, room air changes, hand hygiene, visitor traffic. And we correlated all of those building metrics. We had about 8,000 points from the building. We correlated them with almost 400 patient outcomes. We collected all this data, sent it off to our statistician. So think about which of those you think might be the most impactful for patient outcomes, specifically for these infections that we get in the hospital. Well, we got our results back and we were startled. Our statistician told us that an independent variable was dry air in the patient room. It was correlated with more infections. So we thought this was absolutely wrong. If anything, we thought, well, higher relative humidity would be associated with more growth of organisms. But in fact, what we were told was the opposite. We didn't believe that, so we got another statistician, found out the same thing. We also found from the microbiology studies that as the relative humidity approached 42%, which was as high as it got, the diversity of the microbes in the patient rooms also went up. So we saw a correlation between relative humidity, a little bit over 40%, with greater diversity of microbes in the room, which is good, and with better patient outcomes. Conversely, when the relative humidity drifted down, 30%, we saw more infections and less diversity. I was still skeptical, so we did another study in a long-term care facility and found the exact same thing, that when the indoor relative humidity in a long-term care facility was maintained between 40 and 60%, we had less pneumonia, fewer viral outbreaks of pulmonary disease, and we had fewer gastrointestinal infections, norovirus, notavirus, C. diff. In addition, skin infections were lower. We had improved healing of pressure sores in these patients. So again, these are correlation studies. We cannot at this point talk about causation. Then a group from the Mayo Clinic came along and decided to look at influenza transmission in a preschool. So they actually took this study a step further. They humidified half their school, let the other half do what happens in the Mayo Clinic area, northern Minnesota, bring in cold air, heat it up, and unless you add humidity, you're going to drop your relative humidity to about 20%. So what this study showed was that in the dry part of the school, there were more infectious particles in the air, the viral particles were more virulent, and the rate of absenteeism in the non-humidified part of the school was about 3 times the rate of the rest of the school. So the part of the school that was humidified to 45% had much cleaner air and fewer absent children. So let's talk about microbes in a building with different amount of water vapor. If somebody sneezes or coughs in the room where you're sitting, what are the chances that you're going to get sick? And how does the building influence that rate of illness? So in a dry building, if someone coughs, droplets exit their airways, their mouth, their nose, about 85 miles an hour. And when it's dry, the droplets quickly desiccate. So at 20% relative humidity, within a matter of seconds, a 1 micron diameter droplet comes out of your mouth or nose and shrinks rapidly to become about 0.5 microns in diameter, which is known as a droplet nuclei. We now know that droplet nuclei can travel upwards. They're very buoyant. They travel through the HVAC system, and they can remain in the environment for not just days or weeks, but even years later. We used to think, before the metagenomic tools were used, that these tiny droplets were not infectious because they're very hard to grow in tissue culture. But we now know that, in fact, many of them are even more virulent than they were when they first exited the person's airways. So we need to consider what's happening to these droplets. Studies on guinea pig and influenza A shows that viral particles that are in droplets are highly infectious at low relative humidity. But when the relative humidity reaches 40%, the infectivity plummets rapidly. Within 15 minutes of being in a relative humidity of 40%, 80% of the viral particles are no longer infectious. That's remarkable. So for many organisms, at 60%, the infectivity will go up again. But there seems to be this sweet spot for decreased infectivity of viruses and many bacteria between 40 and 60% relative humidity. Pathogens are less infectious. We used to think that those tiny particles, 0.5 microns in diameter, were just particles, and unless you were a semiconductor or a circuit board, you didn't really have to worry about them. But we now know, through metagenomic analysis, that those little tiny particles are often still very infectious. And they're hunkered down in a protected spore form, waiting to infect a secondary host. So this has really been a game changer in understanding how important the airborne environment is in disease transmission. Let's review why microbes in a dry environment are more pathogenic, more disease-causing than microbes in a indoor environment with a relative humidity 40 to 60%. So one, the droplets shrink down and can travel far and wide and infect secondary hosts that are very far from the first person who is sick. Number two, it's very hard to clean surfaces when you have continual resettling and recontamination. And thirdly, for reasons we don't yet understand, and I read Nature and Science, these top biological science journals, avidly, and we're still struggling to understand this third part, and that is that bacteria and viruses in the airborne state are more infectious than those organisms in a well-humidified building or air. So what happens? Well, when we've analyzed microbes coming down from the space station where there's very dry, desiccant conditions, we can actually study the effect of ultraviolet light on organisms. But what we've found is that organisms that have been exposed to this dry environment have increased virulence and increased rates of antibiotic resistance, even in the absence of antibiotics. So think about everything we read about the problems with antibiotic resistance, because we have taken too many, we use them in agriculture. But what we're finding is that bacteria that have become resistant to medication, they can actually pass that genetic material back and forth when they're in the airborne state. And the degree to which this is true really became clear in July of 2018 when a new staining technique was perfected that showed the actual transference of antibiotic-resistant genes. So what I'm telling you is that it's not just having a cut, taking antibiotics, and having your wound recolonized by resistant organisms. We're transferring and increasing resistance through the air. And that's something we really need to pay attention to. So for example, in a hospital, you may be aware that ASHE, American Society of Healthcare Engineers, and ASHRAE's followed suit, have decreased the allowable relative humidity in operating rooms from 35% to 20%. So they've said it's okay to make your operating rooms drier. The reason that it's okay is that surgeons have multiple layers of clothing on, so they're warm, they want the operating room cool, they want the sensible temperature low, and it's harder to control liquid condensation in a cool room. So the surgeons act like they are the end users of the operating room. But unbeknownst to us until recently, when the air is dry and cold, number one, the patient's immune system is impaired. But secondly, an excellent group out of Indiana University has shown that the sterile field at 20% relative humidity is less sterile than when the relative humidity is 35%. And they've furthermore done studies, and you'll have those references available to you, that show that you can turn down the room air changes in a hospital operating room. They're repeating the study, but instead of running your room air changes at 30, you can reduce those to 15 and still have a cleaner, sterile field when you maintain the relative humidity. So that's a key area for energy savings. Now that we are seeing an increase in antibiotic resistance and we're studying how that occurs, we've learned that when bacteria become airborne in droplets, they have increased transfer of antibiotic-resistant genes. So this means that in a dry environment, such as a hospital or an office building near your home, droplets become airborne if they contain bacteria. Those bacteria can share their antibiotic-resistant genes while in the airborne state. And this is known as horizontal gene transfer. It's very rapid and very effective. With all this information I'm telling you, you probably don't want to rely on one or two studies. So included in this presentation, you will have lots of references that you can look up. Some of this material is new, some of it we've known for quite a while. If you actually go on the CDC website and look for airborne transmission, you'll see a limited number of illnesses, things that we're pretty familiar with: SARS, measles, tuberculosis, influenza. However, if you expand your definition of airborne transmission, and thankfully ASHRAE has now done that. So the ASHRAE Technical Committee 9.6, infectious disease, doesn't just talk about airborne transmission. They talk about transmission of infectious aerosols. So with that expanded concept, we now know and are finding that all sorts of diseases are transmitted through the air, things that we didn't used to consider. So we now have to think about MRSA, other kinds of Staph aureus, Clostridium difficile, even the RNA viruses, which includes Ebola, we now know can be transmitted in droplets. So this is a critical component of disease transmission that we have to address. So let's think about human beings indoors. Take somebody about my size, say a 50-kilogram woman. How much surface area do I have that's in exchange with the indoor environment, with the potential to lose moisture? So frequently we think about our exposed skin, which may be, 10 square inches. But in fact, a 50-kilogram person has the surface area of about half of a tennis court, with the doubles, alleys included, that is available to lose moisture to the environment. So if you're a 100% saturated human being, and you're in a 20% relative humidity room, as the universe moves towards equilibrium, the second law of thermodynamics says, as we increase entropy, the air is going to try to reach saturation. So what does that mean for the person? It means that moisture is going to be removed from your body through your skin and through your airways to supply the air in the building. It's not personal, but it happens to everyone. So what does that do to us? A great study came out in May 2019 from Yale, where genetically engineered mice were used, mice that respond to infection and to influenza exactly like humans do. They were used to study what dry air versus humidified air does to the immune system. And what the immunobiology group at Yale found were a couple things. One was kind of expected, that the mucus lining your respiratory tract from your throat down into your lungs, that mucous membrane becomes more dry. The fluid overlining the cells becomes more viscous, and these little hairs called cilia, which protect our lungs from deep settling of bacteria particles, cannot work. So dry air, you thicken up your respiratory mucus, the cilia don't work, and particles settle more deeply in your lungs. If you think about your lungs, between the air exchange, so oxygen, CO2 transport, and your blood, there's only one cell membrane that separates your airspace from your blood. So if something goes from your lung into your blood, you now have what's called sepsis, which is really not good. You don't want to be septic. So when you dry the mucus out, the cilia can't work and you're more vulnerable to things settling deeply in your lungs. So that's one of the findings from the immunobiology lab. But surprisingly, there are other findings that are remarkable and have implications for other diseases that we're seeing an increase in. For example, in the mice maintained at 20% relative humidity, when tissue damage did occur, they were not able to synthesize some of the protective proteins that we make in our bodies to help heal inflamed tissues. So, for example, interferon wasn't produced at the same rate. And the scavenger cells that help clear up any kind of damage, cells called macrophage, big eaters, The macrophages weren't functional in the lungs of mice in dry air. So if you think about the overall impact of the moisture in the air on the first arm of our immune system, which is the general protective effect, we now know that our body cannot fight off foreign particles or invaders as adequately when we're in a dry environment. So what does this mean for allergies, for autoimmune disorders, where our body doesn't regulate the difference between our own cells and bad cells or bad things? So as you think about the seasonality of autoimmune disorders, we see a higher rate of things like Lou Gehrig disease in the winter, and we see a disruption of the immune system. How much is this related to the lack of water vapor in our environment? This is a topic that's being researched very energetically right now. So we've been talking about the increase in infectivity of organisms in the air. We've been talking about increased antibiotic resistance, spread through airborne organisms. And so how does this apply in the real world environment? So going back to a hospital, if you look at the 7 most common organisms that cause these infections that kill us, all 7 organisms survive quite well in these desiccant conditions. So we're now seeing a correlation between what we're finding in the lab or with animal models and what's actually happening with patients in the hospital. So a dry indoor environment leads to increased microbial virulence, and now we're seeing increased infections in our patients. So we really, this is exciting. It's kind of scary, but it's exciting because we've identified a problem and it's one that is actionable. Okay, so we've been talking about microbes. Let's talk about human beings in these environments. So we cannot just shrink and float away through the HVAC system if we're dried out or dehydrated. We have a skeleton. We can't wilt like a plant does. So what happens to the human being in a dry environment? Well, as we lose moisture, so what happens to us occurs throughout several different systems. One, our brain is affected, even with mild dehydration of 1.5%, which most of us probably are by 2 o'clock in the afternoon, unless you've got an IV going. By 2 o'clock, we're slightly dehydrated, and what happens? So functional MRIs of the brain have shown that we become more fatigued, our hand-eye coordination decreases, our concentration lags, and we might become more anxious. And this all occurs at a very mild level of dehydration. Your urine is not even darkening up at this point. If you go to the bathroom, your urine will still look very light colored. But yet, that level of dehydration is having an effect on us. I got a call from a number in Washington, D.C. about 1.5 years ago, and it was from the General Services Administration, branch of the NIH. They were concerned because they did a big study over 400 government buildings, looking at the decreased productivity and the stress level in their government employees. And they felt like something was going on in some of their buildings that was harmful to the productivity of the office workers. So they did a big study looking at indoor conditions such as levels of volatile organic compounds, looking at acoustics, looking at carbon dioxide, views of nature, lighting wavelength, proximity of your neighbor, humidity, sensible temperature. And then they correlated those measurements with levels with physiological stress measurements. So they looked at heart rate variability, they looked at cortisol levels in the people's saliva. When you're stressed, your body produces cortisol. So they looked at a number of parameters, got their results, and called me. And they said, we have found that if the indoor relative humidity is less than 35% or over 60%, our workers are stressed and they're less productive. I didn't make any comment about working for the government, but they decided to look more into the concept of these people being fatigued. So they also did a study where they wired people up as if they were being evaluated for sleep apnea. They sent them home with these machines, And surprisingly, they came back with results showing that when the office environment is dry, people weren't sleeping well at home at night. This was an excellent study controlled for activity, season, body index, body mass index. So something that happens in the office during the day was impairing people's sleep when they were in a dry environment. So we now actually know more about that. We have learned that your skin produces hydrocortisol, which is a stress hormone, when you're in a dry environment. This is very new data. We never before knew that your skin could produce cortisol. We thought all the cortisol in your body came from your adrenal glands. We now know that if you're in a dry environment or exposed to ultraviolet wavelength, your body produces cortisol from the skin. So this decreases your immune system, it interferes with your sleep, and it makes you more vulnerable to skin cancers. Not surprising, our skin is the interface between the outdoor environment and the indoor, but we didn't know about the cortisol piece until recently. So once again, this is another part of how a dry environment harms us. Let's talk about our respiratory system now. So Dr. Akiko Awasaki at Yale just published a landmark paper May 19, 2019, where she wanted to answer the question of why exactly does dry air result in higher influenza disease rates and more severe disease. So she did this study in genetically engineered mice that respond just like human beings to influenza A, which is the seasonal influenza. So she found some fascinating things. Using this mice model, she found, not too surprisingly, that the mice at 20% relative humidity have their mucous membranes of their airways slightly dried out. So we all have a layer of mucus from about our back of our throats down into our chest. And in that layer of mucus in our respiratory tract are little hairs called cilia that are constantly washing upward. And these cilia prevent particles from settling deep in your lungs, where there's only one cell membrane that separates your lung cavity from your bloodstream. So you don't want particles and bacteria getting down there. And the mucus and the cilia help prevent this. So she found that the mucus is a little bit more viscous and the cilia can't work as well, and particles settle more deeply. But she also found that the body cannot repair any tissue damage adequately in the drier environment, and that these proteins that we normally produce, such as interferon, that help our bodies repair tissue damage, the production of those proteins is impaired in dry air. So now let's think about, okay, what does this mean for our skin, and what does this mean for this increase in autoimmune disorders that we're seeing? If particles from the outside get deeper into our skin layers or into our respiratory tract, and our body recognizes those as foreign, we don't process that information properly, and we're seeing increase in allergies and autoimmunity. So this is an area of active research, but again, it points to the importance of water vapor in our environment. As human beings, we were not designed to live in the Sahara Desert all the time. So let's think about this. Is this new information? Well, some of it is, but some of it isn't. If you think back to the Sterling-Avondale chart from 1985, wonderful graphic showing that there's a 40 to 60% relative humidity sweet spot. It's great for human beings and decreases problems from pathogens. So I took all of our new data, all of our metagenomic analysis results, and put them into a similar format. And once again, 40 to 60% is the ideal water vapor relative humidity level for humans. Where humans are healthier and we have more healthy microbes and fewer pathogens. I've been telling you some pretty dramatic and remarkable statistics and things that we can act on. Is this all new? The fact is, it's not all new information. If you think back to 1985 to the Sterling-Avondale chart, it's a very clear graphic that reveals that 40 to 60% relative humidity is beneficial for humans. That seems to be the sweet spot where we have fewer problems from allergies, bacterial infections, viral infections, even ozone health-related problems. That's 1985. If you fast forward to 2019 and put all of our new data into a similar format, we're finding that 40 to 60% relative humidity is great for people. And it also diminishes the pathogenicity of bad microbes. So if we've known this, why aren't we humidifying all of our buildings? Well, there are a couple reasons for that. One, there's a divide between clinical people, physicians, nurses, infection preventionists, and building professionals. Clinicians we're now saying protect the occupants, we need water vapor. Engineers, architects, builders say the only good humidifier is one that's turned off. It's easier to dry out the building than to create new walls and new envelopes. A lot of people think that mold can actually extract water vapor from the air, and that's incorrect. Mold or fungal organisms need liquid water to grow. But so if you're in a cold climate and you have 40% indoor humidity and say 10 degrees outdoors, and if you have say a 2-layer piece of glass in your window, you're probably going to have some condensation that will then ultimately result in liquid water, and you can have mold growth. And yes, that's true. But the solution is not to dry out the indoor environment. The solution is to create your building envelope and your insulation around ducts and pipes in such a way that you have a good thermal R value as much as possible, so you don't have high water activity in interstitial spaces. There's certain buildings where the relative humidity is maintained 40 to 60%, and those buildings are places where the business model, the return on investment, is clear. So if you're a research animal at the NIH, and if you die and you cost $20,000 to replace, you're going to be in 45 to 55% relative humidity. NIH knows that that's the level of water vapor you need to protect from disease. If you're an astronaut and it costs a lot of money to train you, NASA knows how to get water vapor up into the occupied parts of the Space Center. If you're the Mona Lisa or a rare book, you're going to be in a great environment, or a circuit board. But what about the rest of us? Do we have a value? Yes, we do. Sometimes that's only seen as cost avoidance. So if a building or a business is losing money because you're not productive, you're going to be costing money, and it behooves that building owner to improve your environment. The hospital where we did the study lost over $15 million in 1 year in non-reimbursable care for infections that they caused. They also tied up 11,000 patient bed days with non-reimbursable care. That is a big price tag for a hospital. Unfortunately, it's difficult to get those data points, so there are few of these studies, and we definitely need more. So we've talked about a number of concepts that are probably new. We've talked about the fact that microbes are all around us, in us, and on us, and that we're actually more microbial than human. That's new. We've talked about what that does to our concept of hygiene, that maybe we need to diversify the microbes in some environments rather than restricting the communities. I wouldn't propose that in a bone marrow transplant unit where you have no immune system, but in your home or offices, let's think about what we're doing to the good microbes so that we're not just eradicating what's beneficial to us in our misguided attempts to kill all bacteria. We've talked about that. We've talked about the need for moderate indoor humidity levels. That's not something that we often think about. However, if you humidify your home, you might realize how much better you feel with moderate humidity levels. And we've talked about the value of human beings in buildings. So these are all this is a different way of thinking. It's different to ask engineers to begin to think about health. ASHRAE is actually defining health. What is the definition of health? Is it absence of disease? As a physician, I think about vital signs, I think about blood chemistry, but those aren't metrics that most non-physicians or non-clinicians are used to thinking about. So as ASHRAE has expanded, even this tech hour, as ASHRAE has expanded its purview to include occupant health, we need to find ways to monitor this new building metric. In conclusion, what we've learned from the hospital environment and from schools and some offices are actually findings that are applicable to all occupied buildings. So our homes, everywhere where we spend our time indoors, will benefit from proper humidification. And you, building professionals, are in a great position to affect these changes. Thank you.